We have a new friend of Ecosummit, a very important person, Professor Dr. Juergen Schmid of the Fraunhofer Institute for Wind and Energy Systems. And he's talking about how we can transform our energy system into a 100% renewable energy system. Please come on stage, Professor Schmid. Thank you. Hier, genau.
Yeah. Okay. Good morning, everybody. After this brilliant presentation, it's really hard for me as an engineer to also try to look into the future. But I will do this based on technology which is relevant for renewable energies. So I will be talking about possible developments in the transformation of our energy system. I will begin with the reason why in the energy sector we have to change to sustainable systems. Then I'm going to speak about the potential. It has been mentioned before, the potential of the different renewable energy sources. Then, as an important element, I'm going to talk about efficiency, because efficiency and renewable energies, those are the two pillars of the future energy system. Afterwards, we are discussing the way on how to stabilize our electricity grid, since, as you know, photovoltaics and wind, they have a fluctuating power output, how to stabilize it and to equalize the production in such a way that we can keep a secure power supply for the consumers. And finally, I'm going to talk about the cost, about the economics, and I have some surprises for you in that sector. Let's begin with this diagram, which shows three curves. The green curve here shows the power consumption, the global power consumption worldwide over the last 100 years. And what is disappointing is the red curve. This is a CO2 concentration above the steady state level, which we had thousands of years before. And you see quite parallel development. Both curves are increasing exponentially. Exponential growth is the most difficult one because the growth goes faster and faster, yet more you go to the right side. And the blue curve shows you the world population increase, which is a further indicator that if we continue like in the past, we need more energy. People which are already on the earth, they would have a better life, which in the past was identical to needing more energy. So the job we have to do is not only to stop this exponential growth to a plateau, but to reduce it even, and this seems not to be an easy task. Some simulations of different colleagues have been done in the past, and in this diagram you can see some results of the simulation, how the energy transformation should develop. On the left part you can see the last period, which where you can see the different contributors down in brown. This is oil and coal here, then gas and renewable energy, water power, hydropower, and other renewables. So this was the past on the left side, which shows that here we had some biomass utilization, but it becomes smaller and smaller, and today the contribution on a global scale is really small. On the contrary, if you look to the right side, first of all, the exponential growth could be stopped, and in some cases even be reduced. The reason for the different scenarios was that some groups developed those scenarios under the assumption to have a high share of nuclear, a high share of biomass, and so on, or CCS, that means carbon sequestration using conventional power stations for the electricity production. And the right bar is the scenario of the Advisory Council for the German government, where I am also a member of, and we have developed the scenario under the assumption that we would have no nuclear energy at all and no conventional fossil fuel. That means 100% renewable energy scenario. You might be surprised that the absolute value is lower than the value of today, and I'm going to show you why this can be done using all effects, all elements. But first of all, I would like to come to the potential of renewable energies. Is there enough potential available? And when I began my career in the solar energy sector, we had to deal with the question, well, can we supply 2% or 3% of the consumption? Now we are sure we can supply 100%, and how this looks like can be seen here in this detailed scenario. First of all, this scenario on the left side is the same as was given by the International Energy Agency. Here we are today. And if we continue, then we would arrive at that dotted line with an increasing power consumption. And here on the right side, if you look into detail, you have no longer any conventional energy. And by the way, the nuclear energy is by far overestimated. It's a yellow color here in the world scenario, and you can see how tiny the contribution of nuclear energy is at all. On the right side, you see a bunch of renewable energies supplying all needs of the world, but we have some white fields here which are equally important, because the difference between the business as usual and the real consumption here at this point is more than a factor of 2, and that is caused by efficiency. Here are the potential contributions of different renewable energy sources, beginning with the black bar. This is the world's electricity consumption. The value is about 20,000 terawatt hours. That doesn't mean anything. So if you recall the 20 and look to the potential of wind energy, that is 800. So we have more than enough wind energy potential to cover all the needs of the electricity consumption. And this tiny part is already used today. So we see there's a lot to be done in that sector. The situation is nearly identical for solar power, bioenergy, and marine energy. That means energy from the ocean. As a consequence, we can state there is no scarcity at all when looking to the renewable energies. We simply have to exploit them, and how this develops, I'm going to show it to you. But before, I would like to explain you why the introduction of renewable energies is increasing the efficiency of the whole energy system. Let's look to the first picture. On the left side, we show the energy pattern of a conventional electricity production power plant. As an input, mostly coal, we have such a lot of input to produce 1/3 of electricity. 2/3 of the energy is being wasted from the heat, that's waste heat. Now, if we are changing our system from coal-fired or thermal power plants into the direct use or direct production of electricity, by means of wind, of photovoltaics, or of hydropower, there is no waste heat at all. That means this part of the input needed for the coal-fired power plant is simply not necessary. And that is one of the reasons why a reduction of the primary energy demand is resulting without reducing the electricity consumption on the other side. And this might be important for other conversions, as I'm going to show to you now. But here in this example, you can see the consequences of this shift for the European electricity system. Today, we are producing this amount of electricity using this amount of primary energy in the form of coal, mostly in the form of coal or nuclear energy. That is useful electricity, and the blue part here, this is the waste heat, which is useless. Now, by introducing more and more wind and solar, we are reducing the primary energy demand, despite the fact that the electricity consumption is increasing. And at the end, by mid of the century, we have nearly an identical relation between primary energy demand and electricity generation. Even worse, or even better, is the consequence for the CO2 emissions, because coal-fired power plants do emit a lot. They are emitting about 1 kilogram of CO2 per kilowatt hour of electricity. A windmill or photovoltaic system does not emit anything, and as a consequence, the CO2 emissions are being reduced dramatically this way. Now let's look to another sector, which is at least very important in Europe and especially in Germany. That is the heating sector. Today we are heating our buildings using oil and gas for our heating system. This has to be transformed, and one of the possibilities is, of course, to use the waste heat from power plants. So this can be used, but an even more interesting application is now heat pumps. Heat pumps are a very well established technology. They had no advantage in the past, but now with the transformation of the electricity system, the heat pumps are becoming more and more attractive in terms of efficiency and in terms of CO2 emissions. As you can see in the next slide, hopefully. Yep. In this diagram, you can see here the CO2 emissions per kilowatt hour of thermal energy from the oil-fired boiler, from natural gas condensing boiler, and from electrical heat pump. You can see today the heat pump is a little bit better than those alternatives, but with the transformation of the electricity system, the heat pump becomes better and better and is the technology for the future. So for you, as a potential startup to look for new applications, electrical heat pump is a very extremely interesting technology for the future. The third sector, which is equally important and the most difficult one, is the transportation sector. Only a few of you might know that only 20% of the energy input of the fuel is being converted into shaft power to drive the car. The rest is lost heat, waste heat, which cannot be used otherwise. And by changing the conventional piston engine to an electric drive, you can omit all these losses associated with a piston engine. And also here, when looking to the whole system, you can see how electric vehicles, which have a lot of emissions today because the electric energy is mostly produced by coal-fired power stations, is being improved through the conversion of the electricity system. The solid line is a direct emission of a gasoline, of a diesel, of an electric car, and the dotted line here is the result if you take into account all other effects, maybe, for instance, to produce the car or to do the treatment after the lifetime, after the car. But clearly you can see that the electric car has a highest potential to come down with the CO2 emissions through the conversion of the electricity system. Now, quite often it is argued that biofuels could be an alternative to reduce the emissions, which is only partially true. It's a very dangerous game for two reasons. First of all, biofuels have emissions in other sectors during the growth, during land use change, and so on. We have investigated the emissions of biofuels compared to fossil fuel, which is the dotted line here, and you see some bars are above these dotted lines. That means using this kind of biofuels is producing more CO2 emissions than the alternative of having a conventional car. Some are quite attractive. They have a drastic reduction, for instance, palm oil on degraded land, but we also found that application of biofuels in other sectors, like the electricity production, has by far better effects than using it in cars. As a consequence, we have been proposing to the German government to stop all activities, all support for biofuel production, including research and including the application. This I will take. Now we come to one of the most important parts, and that is the balancing of the electricity system. How can we balance it? And to begin with, I would like to show to you this diagram, which shows on the left side the map of Germany and the different wind speeds. Then we have here the irradiance over Germany over the days. Here we can see the consequence of power production on different locations, and here down is the fluctuating energy over the time. So this is always one day, and you can see the red curve is the load, the demand, and the blue curve is the contribution of wind onshore. This kind of blue is offshore, yellow is photovoltaics. You can see that on some days those power sources can supply nearly all the load, even in 2020, and later on we will find a lot of surplus. And the question is, how can we compensate for the deficits here and for the differences if we have surplus energy or a deficit in the system? A first kind of an approach is a non-decentralized solution. It's a big grid, a kind of a super grid spreading from Scandinavia down to northern Africa, which equalizes the flows of the power, or in other words, somewhere in Europe the wind is always blowing. This is an important step. It's the cheapest one to equalize, but it's not enough. The next step is to combine the different renewable energy sources, photovoltaics and wind and biomass and hydropower and some storage to approach the load profile. This also helps a lot, but it's also not sufficient. Now the third kind of stabilizing the grid is quite important, and it's becoming more and more important. That is that to allow the load to follow what is offered, to follow production. This is the first time where load is able to follow production. To be able to do so, loads need some information. Thanks to the modern information technologies, we can provide the information, and the loads can be made intelligent enough to decide when they would like to consume electric energy and when they stop the consumption if there's a scarcity in the electricity supply. Thanks to the intelligent electricity grids, the smart grids, we have the information for the consumers. It's a two-way information system because the consumers, they also can get into dialogue with this cloud. Here on the right side, you see a laboratory, our laboratory, where we have set up 2 households of the future combined with smart grids. And in real time, we are currently building up about 1,000 households or equipping 1,000 households with the smart elements to become smart consumers. There is one thing left, and I can quickly go over. We have periods of time of about 2 weeks which we have to overcome, and this is not possible by means of load management of the big grids and so on. We need a new way of storing energy for longer time. This will be done by a new approach, which is methane. Methane is a chemical storage means, and you are going to get very much more information on this technology tomorrow by Mr. Rieke from the Solar Fuel Company. That's why I can go over this part and use the rest of the time to talk about the cost of renewable energies. On the left side, we can see the electricity production cost of wind energy, minimum and maximum, depending on good or bad sites, compared with a coal-fired power plant, including emission certificates. And you can see clearly that a very well-sited wind turbine can produce electricity today for a cheaper price than a coal-fired power plant today. So that means the cost of introducing renewable energies is not necessarily higher today than the alternatives. And since those technologies follow a learning curve, making them cheaper and cheaper, the consequence is renewable energies will become even cheaper. We have investigated this investment cost for Germany, and we can see in the electric sector we have to pay additional money for photovoltaics, wind and biomass, arriving at a level of nearly 15 billion euros per year. But after 15 years, renewable energies become cheaper. That means we have to invest a little bit more in the next 15 years. In total, it's about 200 billion. But if we make a balance sheet, after 40 years from now, we have gained 700 billion of euros for the German electricity system alone. I'm coming to the conclusions. Yes, we can transform our energy system completely. Efficiency is an important element to reduce the total energy consumption. The introduction of renewable energy systems provides the biggest contribution to efficiency gain, and the cost for the introduction or for the transformation of the whole system seems to be very limited for the next 15, 20 years. Afterwards, the new system becomes cheaper and economically attractive compared to the today's system. So it's very worthwhile to go into that new field because you can make a good business with it. I thank you for your attention.
So if there's only one way into the future, it must be the renewable energy system. Summarizing, how long will it take for Germany to create almost 100% renewable energy system? What is your forecast?
Yeah, well, there are two scenarios. First of all, the energy scenario of the German government, which has stated that Germany is expecting to have an 80% contribution by mid of the century in the electricity sector, and 60% for the whole energy sector, including transportation and so on. We have investigated the possibilities of having 100% renewable energy supply scenario by mid of the century, and I'm convinced it's easily possible, but we have to start fast. And we are on the best way.
That's why we are here. Thank you very much. Due to time, advanced time, we skipped the questions. One more round of applause for Professor Juergen Schmid. And,